Let me thank Chetan, Justin, and Aninder for inviting me here to this weekend conference. It's an interesting idea. So I'm going to talk about something which 75% of this was covered a couple of months ago in ICTS, but there's 25% new. Okay, so the idea is this is one part of this has already been published. This is about the anyway. So and then there's some more work. So the first two are about the two-dimensional string theory and matrix quantum mechanics, and then there is some work in progress with Nemani about the granularity, granular geometries in the context of giant gravitons, and there is something about just the random matrix models, not matrix quantum mechanics, with these people, and these are based on techniques that have been developed over several decades. Okay, so let me go to the motivation. So it's now been 3 decades of holography. If you start with C equal to 1 matrix model, being dual to two-dimensional string theory, that's 1990. BFSS matrix theory, dual to M theory, that's 96. And of course, ADS-CFT. So it's a good time to ask what we have learned about emergent gravity. These are all examples of how we can think of gravity being emergent from these sides. These are all, as you would notice, these are all matrix theories of some kind. Matrix just random matrix model, matrix quantum mechanics, multiple matrices, and matrix fields. So a difficult conceptual issue about general relativity, including higher curvature corrections, has been that of infinities. So you can talk about infinities, which are like singularity of classical solutions or divergence in the quantum theory. So it's been sort of thought that these infinities can be handled by using a different description at short distances, and there are various ways one can say this. So what we will do here is to find for two-dimensional string theory that such a description arises, in fact, emerges from the C equal to 1 matrix model is in terms of a granular geometry, and I'll explain what that means. So in little more detail, one matrix model so here I mean matrix quantum mechanics, a single matrix function which is a function of time in the large n limit is traditionally described by continuum field, which is the eigenvalue density rho of lambda. So the matrix first of all is given in terms of the matrix elements, and then in these models you can reduce them to the n eigenvalues, and in the large n limit, the distribution of the n eigenvalues you can try to capture in terms of some continuum field, which is eigenvalue density, described by cubic field theory. So this is the what is also called the collective field description of the one matrix model, in particular the C equal to 1 matrix model. So in these works, rho lambda, this eigenvalue density, is identified with the continuum field of two-dimensional string theory. So that's the duality. It's a massless scalar field, which is called tachyon. Some historical abuse of the name tachyon, which is the only propagating field in the two-dimensional string theory. So I'll take this massless scalar field as sort of kind of substitute for propagating gravity fields, because the usual gravity and dilaton are not propagating fields in 2D. So I'll take this massless scalar field as the propagating field and try to understand some statements about this as if this is the graviton. Okay, I'll explain what I mean. So now, so this description actually works for tree amplitudes which correspond to the leading large n behavior. So if you take an effective theory of this density field, okay, which is called a collective field theory, in that you can compute the 4-point function of the density variable. So just corresponds to some. So there, later on, I'll explain how the density variable theory looks like. It's a cubic field theory actually, and I shouldn't have written this. It's a cubic field theory, so it's sorry about this cartoon. This is the wrong cartoon. So the 4-point function can be computed from the effective field theory. 4-point function can be computed from the C=1 matrix model directly, which corresponds to a fermion. The C=1 matrix model becomes n fermions. So you can directly compute in that theory this stuff, and you can also compute the 4-point function of the string theory side, which is the 4-point function of tachyons in the in this 2-dimensional string theory, and they all match. They all match. Okay.
Time ordering here.
There is time ordering. No, this is just a very you can also do a Euclidean calculation.
They match, but please tell me later. But is there some issue about some leg poles or how to?
The matching is with that understanding. Yeah. So yes, absolutely. No. There's not. So that's coming. Okay. Now that was the leading answer. That's tree level. So that's leading large n. How about loop amplitudes? So you can compute here. Okay, here this cartoon is okay. It's using 3-point vertices. So you can compute 2-point function of rho at one loop, which looks like this. So this is divergent. I mean, it's a cubic field theory, and it has derivative couplings. So you can easily do power counting. It's power counting divergent, and is actually divergent also. You can do that computation. This computation was done by these people in 91. And in fact, we right now we are revisiting this computation to see various issues of counter terms and so on and so forth. It remains divergent. Okay, so you should think of this as the ultraviolet divergence of gravity. It's like a graviton loop. Okay, we don't have a graviton here. We have this massless scalar field, but that sort of we take that as a poor man's substitute of a graviton loop. So it's divergent. Now, however, you can do this computation in C=1 matrix model, and that's convergent. Okay, I'll explain later on how from the fermion theory it's sort of more or less obvious why it is. So I would probably not have time to do this calculation for the 2-point function, but for the 1-point function, I'll say in some detail why this is divergent, this is convergent. And the 2-dimensional string theory result is also convergent. Okay, that's the usual ultraviolet finiteness of string theory. So that's this matching has been done by Yin et al. in 2000, I think it's 2018. Okay, and so therefore clearly, this kind of effective gravity theory is not doing the job. Okay.
But this left-hand side doesn't have any finite piece which will match.
Left-hand side, you mean whether I can do some counter term subtraction and so on? No, it doesn't. Okay. So
I have to ask, although you will come to it.
Yes.
It's finite on the fermionic side because of the cutoff implemented by
the
finite
depth,
n.
exactly, the finite depth of the Fermi C. Yeah, finite n. However, we are talking about C equal to 1, so n is actually infinity. But this finiteness survives double scaling also. That's something quite interesting. It's not immediately obvious. So these are yeah, exactly. Okay. So now, so what do we do? So what I'm going to say is that there is an alternative, gravity, quote unquote, description. That's a lattice boson. So, okay, so it's like a lattice massless scalar field, lattice scalar, which makes it finite. And it also agrees with the fermion theory and the two-dimensional string theory as a result. Okay, so here it is. So what do we replace it by? So it's a lattice theory, lattice scalar, and it's convergent, and here it is. It's equal. Okay, so these things are equal. If I replace the density variable by a different boson, it's a lattice boson, exact lattice boson. So this was about a loop amplitude of the one loop order amplitude. In fact, we started this work with in order to understand some similar puzzle that happens with entanglement entropy. This is some calculation that was done by Schmidt in '95, revisited by Hartnell and Mezenc in 2015, and so the result. Okay, so let me say. So the C equal to 1 matrix model result was computed by these two groups, and it turned out to be convergent. And let me say what I'm doing here. So the fermions. Okay, so the eigenvalues are real numbers. Okay, and I'm going to say that later on, that the n eigenvalues of the matrix, they behave like n fermions on a real line. Okay, now you can say that let me focus on some interval of length L on the real line, and have the system in some state, let's say the ground state of the theory, and ask what is the entanglement entropy of this interval of length L with the rest of the system in a particular thing, and it's given by this formula. Okay, 1/3 log L over GS/LS, where GS is the string coupling and LS is the string length. So this is what comes out of these calculations, and it's a convergent result, as you can see.
So
okay.
You say it's divergent, you mean that the epsilon is just ad hoc?
Here, yes. So if you do the same computation in the rho lambda theory, it is divergent because you need an ultraviolet regulator. Okay. So now the two-dimensional string theory calculation does not exist. Okay. So this is something that should be done. Okay, but it's not there yet. Now what do we say? So these are clearly unequal because epsilon here is an arbitrary regulator. If you have some way to say that, okay, there is an epsilon which is GS/LS, then they agree. Okay, and that's precisely what happens in this theory. Okay, in this lattice scalar theory, what we find is that this epsilon, so it's a lattice scalar with a lattice spacing given by GSLS. That's what we will find. Okay.
So
And
in that sense, I mean, do you expect that in perturbative string theory that calculation can be formulated?
in perturbative string theory, how this GSLS can come is not clear, but I'm going to say, if I get the time in my 2 hours that has been kindly allocated to me, that it's this field, rather than describing a tachyon, okay, a perturbative string mode, it describes D0 branes. Okay, so this is actually a solitonic description of string theory, and perhaps some calculation of that kind might give us this strange GS factor.
So even for this the first expression, this log L by epsilon, if you were to compare the entropy between two different states, for instance, which might not be so easy to do in this formalism, then one would find the same answer. It's only this L independent cutoff that's different.
Yeah, very good point. You could in fact also compute, let's say, mutual entanglement, and that would be independent of the cutoff. But there is still some finite difference between the calculation that between what you find in the rho lambda theory versus.
It's not written on the slide. The slide is
No, in this slide it is a single interval. I have not written the mutual entanglement, which.
I know, but if you did the mutual information, are you saying it seems that the epsilon would just go away?
No, it's not the epsilon difference. There are some finite terms which differ. Yeah, I don't have the slides for it. Yeah, this is actually I should have mentioned that in the work also. There's some finite difference which hangs up between the collective field theory and the fermion theory.
But not your lattice scalar.
Not the lattice scalar. The lattice scalar, of course, we are mutual entanglement. We have not computed using the lattice scalar, but a single interval entanglement entropy we have, and that's yeah. So we could compare between two states also. Okay, but what we have already done, this some work I should have mentioned that with Chintan, where we computed the mutual entanglement, and as you say, the cutoffs go away in the mutual entanglement, but there are differences of finite terms between these. Yeah, it's interesting. We have not completely understood that difference also, but if we do it using the our lattice scalar theory, I believe that we'll get agreement. But this is something that's not done. Okay, so the plan for the talk. So these are done. So I'll explain first. The matrix quantum mechanics, how that corresponds to fermion quantum mechanics, the computation of expectation values and entanglement entropy using the fermion theory as well as the rho lambda, the density variable theory, effective theory. And here, first I'm going to say things about finite but large n. Okay, so. So first I'll describe this, and then because of the differences that we find in this part, I'll then go on to the exact bosonization. So this is in terms of the exact lattice bosonization of matrix quantum mechanics, which works for any n. Okay, And so this would be about n large but finite, and here C equal to 1 matrix model. Here we are going to talk about double scaling theory, in which n actually goes to infinity, and you take some other parameters of the theory going to 0. So n times that parameter is held fixed, okay, in the double scaling limit, and then some conclusions. All right. So let me explain. Consider, so first I'm going to talk about matrix quantum mechanics and computing some 1-point function expectation value of this moment. This is called the pth moment of the matrix. Where so I'm talking about now random matrix which is a matrix as a function of time, and this is the action. There's a kinetic term and there's a potential term, and there's a trace here. Okay. Now you can just do this path integral and see that. Okay. So first of all, because because of the UN invariance of this model, you can clearly go to the eigenvalue description, and at every time point, the measure over the matrix can be can be reduced to a measure over eigenvalues and a Jacobian. Okay, and the Jacobian looks like this. This is called a Vandermonde Jacobian. There are also a measure over angles, but the angles just go out of the thing. It comes out of the path integral because it's we are only talking about singlets here. Okay, but you collect all these Vandermonde factors at every time lattice point, but then because of some other things that come out of the the angular integrals, all the intermediate Vandermonde factors, they just cancel out, leaving only the the two endpoints of the lattice, those Vandermonde factors hanging out. And if you start with some initial and final wave functions here, they are completely symmetric because of the even symmetry, part of which is the Weil factor. So the wave functions which are there at this stage are completely symmetric, but they get multiplied by this Vandermonde factor, so they become completely antisymmetric. Okay. So that's the thing. So it's given by completely antisymmetric wave functions of n coordinates. So they become like n free fermions on the real line with a single particle Hamiltonian. Okay, these are free Hamiltonian. That's sort of easy to see that this trace, it just becomes m dot square becomes lambda I dot square by 2. And these are single trace objects, so there's no interaction. So it's a free n free fermions, and this action corresponds to this single particle Hamiltonian.
What happened to the moment that you are computing that? Should also be there.
Which?
The trace into the power P.
Oh, excuse me. Okay. Yes, indeed. Yeah. So it should become sum over lambda I to the power p. Excuse me. Yeah, it should be there. Right. So now this is a single particle Hamiltonian with some spectrum, which I have called epsilon, and the eigenfunctions of chi n of lambda. For example, if this is a harmonic oscillator, then these are the eigenfunctions, these are the eigenvalues, and if you put n fermions in this states and look at the ground state, then it's just the field Fermi C, like this, from 0 to n minus 1. And you can compute the, let's say for p equal to 4, this is what it would be. This is some small calculation, but this is easy to show how from this thing this object comes. It just becomes like a sum over this quantity for each of the occupied states, and this is easy to compute, and this is the exact result. Okay, this thing. Okay, so that's the Fermion calculation of the C equal to 1. For Fermion calculation of the matrix quantum mechanics calculation, which computes this object for p equal to 4 with harmonic potential. That's it. This is the answer. Now, is there a continuum description which reproduces this? So first we will try, of course, the eigenvalue density description, collective description. So just to say, we will find that this one comes out correctly, okay, but we will find some divergent thing here. Okay, that's what. Okay, so to put the cat out of the bag. Let's try the eigenvalue density description. The eigenvalue density is defined by this, and one is trying a poor man's substitute of integrating over eigenvalues to integrating to a functional integral over the density variable. Okay, this of course is a suspect step, because for n variables here, however large, this is an integral over n real variables. This is an integral over a function. So clearly there is many more degrees of freedom that I have introduced, and what I'm actually losing here are the trace identities. Okay, so I don't have time to go to them now, but basically this row, is actually a sum of delta functions. A sum of delta functions is very different from a function, from a normal function. So, if anything, if I try such a thing, I should do a distributional integral rather than a functional integral. Okay. All right. So since the eigenvalues have become fermions, the eigenvalue density has the following alternative description. This is, psi dagger lambda psi lambda. My favorite chapter in Feynman's lectures in statistical mechanics beautifully explains how this is the same as that. I mean, it's amazing. Anyway, so where I defined second quantized fields, fermion fields, which are defined as so, where psi-n's are the annihilation operators for the mode n, and psi-n dagger are the accretion operators for the mode n. Okay, so what you can do, starting from the fermion theory or maybe starting from the matrix theory, is to try to arrive at some effective theory of the fermions. Okay, which is this. This is a cubic theory in which the theory is written in terms of this zeta variable, which is defined in terms of the rho in this fashion. And if there is interest, I can explain how this comes. Actually, yeah, I don't have time to show this, but you should think of this as like this is like a theory of quarks, and this is like a theory of mesons. Somehow somebody has found this theory, let's say. Okay, basically one way to compute this, the way these people have done. So Daszewicki computed it by making a transformation of variables from matrices to this eigenvalue density, and these people, the way they did that is to start from the fermion theory and compute various correlators of psi dagger psi, okay, from the fermion theory, and ask yourself what is the effective action that gives rise to those correlators. Okay, so you get the same result as both ways. All right. So this is the thing that you can do. So there is some large n factor sitting in front of the action here. So clearly you can do a saddle point evaluation of this moment, trace of m to the power p becomes this integral. Okay, so that's what I need to compute, and I think this 1 over n should not be there perhaps because rho lambda already has it. Anyway, so this is what the saddle point. So you look for a saddle point evolution of this. The saddle point equation is this one, and this is the solution. Okay, the solution is simply, as you can see, that is related to the Fermi surface momentum. Okay.
In the real world, you have 14 minutes left.
Oh, all right. Okay. So this is what the saddle point solution is, and you can compute by this this integral, and it just gives you 1 over 2 omega square, which is the first term of this. Okay, so that comes out. How about the 1 over n square correction?
These variables have the trace identity.
This the rho of lambda, no, it does not satisfy the trace identities, because trace identities are satisfied really by the sum of delta function fellows, and these guys don't. Trace identities look completely weird in terms of continuous function. In fact, even we are going to solve this problem by introducing lattice bosons. They satisfy the trace identity because there's some discrete structure that I must preserve. There is no there is no shortcut to that. Okay, all right. So now the subleading term. Okay, I don't have time, but in terms of this is a cubic theory, and I'm looking for a 1-point function. So clearly it looks like this tadpole. Okay, and it's divergent. Okay, so it's divergent. Here it is. And the exact result was this. Okay, so we don't get it. Okay, so once again we do not get the. Yeah. So so it's not exact except in the n going to infinity limit. So if you want subleading, okay. So we'll resolve this problem by finding an exact transformation of variables from the eigenvalues to a lattice boson field, okay, where the lattice contains precisely n points. But then again, there are subtleties which you have to work out in the double scaling limit, because then the finiteness is not so as a result, this calculation will be in 4 or 5 slides from now. This will be computed by using this one. And the finite number of the finite number of lattice points, or the finite number of modes that will make this thing finite, and this will come out. Okay, and similar statements hold for 2-point functions. Okay, so you can compute 2-point functions in the matrix theory and 2-point functions in the collective theory, and they don't match, and the collective theory thing is divergent. Okay, but this will take much longer to explain. That's why I'm going to stick to 1-point function. Okay, all right, and entanglement entropy. Okay, so this is the thing I have already explained what entanglement entropy I'm computing. So the fermions are on a real line. I'm looking at this interval L, and we ask the question, what is the, let's say in the ground state, what is the entanglement entropy of this interval? So you can ask the question in various ways. So first of all, these are in particles, and we are asking about, so the particles are 0-dimensional objects. So there is no, when we talk about entanglement entropy of particles, we need a different concept. We don't have a bipartition of the base space, because the base space is 0-dimensional for particles. So we can use a new notion of target space entanglement entropy, which with Sandeep, Shumit, and our students we have developed a couple of years ago, and but this turns out to be, because there is a second quantized formulation of this theory as well, it turns out to be the same as doing a bipartition of the base space of the quantum field theory of the fermions, and the result for the entanglement entropy. So first of all, the entanglement entropy is given by this formula, which essentially is like the variance of the number of fermions in the region A, where A is this interval of length L. Okay, so the answer turns out to be, if you have free fermions in a box potential, it turns out to be this, where epsilon is given by L upon n. So there is definite epsilon here, which turns out to be that way. For fermions in an external potential, it's given by this, where the 1 over epsilon is replaced by the Fermi momentum divided by h bar. That's the Fermi momentum. And so here, there are more accurate formulas for this, but we have assumed here that the potential varies slowly inside the interval A. Then you get this. Okay. All right. So
n was the eigenfunction.
n is the number of fermions at the n.
The chi n at the top.
Yes. These are the eigenfunctions of the single particle Hamiltonian. Yes.
For some cases.
Yeah, that's right. I mean, you can, you can actually do this computation fairly easily for this box potential case, but in the other cases also, you can use some large n techniques of Wigner phase space distribution and blah blah. So there are some nice techniques, lovely techniques actually. Okay, so the most recent version of this calculation has been done by Shumit and his collaborators. Okay, all right. So can we get this formula from the density theory? Okay, so let me say what. For a bosonic field theory, such as the density variable theory, this cubic field theory that I've been talking about, there are formulas which allow you to do that computation, and I'm skipping some details, but what you get is 1/3 log lambda 2 minus lambda. This is this L business, the length, divided by epsilon, where epsilon is some regulator, ultraviolet regulator. Okay, this is something that I have already said in my summary thing. So it doesn't agree, because this is actually divergent, but it agrees if you choose this. Okay, so this I have already more or less said.
Sorry, this is if you took your collective field theory and just made it free field theory.
Yes. So how about the full collective field theory? So Shumit and Jevicki in 2022, they have written a paper in which they don't quite compute this entanglement entropy, but something which is a fermionic entanglement entropy, but done in this bosonic language and for free box potential. They find that there is some version of this that comes out, which is actually finite. Here it is indeed. I have taken this to be, but there are regions of approximation where the quadratic, taking just the quadratic part of the collective field theory is good. So this is what you indeed get as a leading result. Okay, so summary so far. Okay, this is just in case Anindya rings the bell. Okay, so a continuum description of matrix models in terms of inconsistent with trace identities, which blah blah. Okay, and it more or less okay. Coming attractions. we'll discuss an exact bosonization of matrix quantum mechanics, how that comes. The boson field lives on a lattice of n points. This is what I call granular geometry, which are in one-to-one correspondence with the n eigenvalues. This new bosonization solves the above mentioned problems, the moment problem and the entanglement entropy problem. And yeah.
You asked me 5 minutes left.
5 minutes left. Wow, wonderful. Okay, so this exact bosonization can be done. So let me tell you. Okay. Yeah. So there is an exact operator equivalence between fermion bilinears. If you have a fixed number of fermions, then fermion bilinears are the only things that are allowed in the theory. The single fermion operators are not allowed because they will change the number of fermions. So this is just a glimpse of how psi dagger m psi n are related in a very complicated way to bosonic oscillators. Okay, and the vice versa. The bosonic oscillators are written in terms of the this one. They look absolutely awful, but they're exact. Okay, and unfortunately I don't.
Delta is a delta function.
These deltas are delta functions. This integer kind of delta functions.
What is the sigma? Sigma k?
Oh, it's just polymetric.
No. These sigmas. Because I have skipped so many things. These sigmas are here they are. The sigmas are related to the these oscillators. So starting from the fermion theory, non-relativistic fermion theory, I have a reformulation of these things in terms of some capital N number of oscillators. So these are like capital N number of modes. Yes.
But the Hilbert space of even one harmonic oscillator is infinite dimensional, and the fermionic system is finite. So something very non-trivial is going on, which encodes trace identity.
So for n equal to 1, okay, that's the let's say these are the fermion states. Okay, so in fact I can invent an A dagger which takes me from here to all the way, and some A which takes me, but you can just define them this way, and lo and behold they look quite weird. Okay, such an A dagger is actually this. Okay, and A is the adjoint of that. So what does this? What do this A and A dagger do? They just take you, from one to the other. It's not a surprise that for a single fermion you have a bosonization. It's not a big deal. Okay, because but it works for two fermions here. A little more weird. The raising and lowering operators have to be done a little more cleverly, and for arbitrary number of fermions also, there is some way. I don't have time to go into this.
So this is
Yeah.
Single fermion is just a 2 or 4, whatever, depending on real or complex dimensional Hilbert space, right?
Yeah, a single fermion. Let's say single fermion, which is in a harmonic oscillator potential. So you have the
Is it fermion quantum mechanics? Sorry.
Yeah, fermion quantum mechanics.
Yeah.
Right. So and then I'm going to put later on n number of them. Okay. So I'm saying that if your n is equal to 1, then that single fermion Hilbert space can be spanned by a single A and A dagger oscillators. Okay. Now if you have 2 of them, then it is more like this kind of stuff. Excuse me, sorry. It is a 2-dimensional thing, right? It's you need 2 2 labels. Okay, for 2 fermions. Okay, namely F1, F2. Okay, where these are the these are the filling numbers of your state, and so it's two-dimensional. So it's not clear that a raising and lowering operators should even exist in a two-dimensional lattice of states. Okay, but they do. Okay, they do. This the second raising operator, ladder operator, goes actually diagonally, and the first one goes up vertically. Okay, these all look very strange, etc., etc. But if you look at how we had arrived at this, is from giant gravitons. Okay, how the dreaded signal has come. So let me tell you. And let me go here. So applications of the exact bosonization. So here's a calculation which corresponds to that the tadpole calculation that I described. Here you can do this exactly. You can see that the number of modes being finite, that actually makes the calculation finite, and it gives you correctly reproduces the matrix model result. And the entanglement entropy, I'll just take. Thank you. For entanglement entropy, there's a conceptual question that because we're doing an exact bosonization of the fermions, okay, clearly any question that you can ask in the fermion theory can be translated to the boson theory. Okay, but the entanglement entropy, including the entanglement entropy, okay, but that question, when you translate it into the bosonic theory, can become very, very non-local, because it's a very non-local thing. So the idea is that, can we get a boson theory so that the entanglement entropy of the fermion theory is the entanglement entropy of some interval in the boson theory as well? Can we invent a real space so that that happens? And in fact, that actually works out. So you can have you can invent a real space which is necessarily latticized, because you have capital N number of finite number of modes, and then you can now, in this theory, you can compute the entanglement entropy of the same. If you had so let me say how that goes. Here it is. So in the fermion theory, let us say that this is the Fermi surface, okay, and basically there is a lattice of bosons that you can invent, in which the endpoints, they basically map to the endpoints of this Fermi surface drawn in the potential diagram, and the density of the lattice points is dictated by the potential. Okay, so this all comes from some W infinity mapping, etc., etc., which I can explain. In case of the box potential, it's easy to explain how the lattice boson comes. It's just this. But in order to go from a box potential to anything else, you can apply some W infinity transformation to get this. From this kind of a lattice, you can get to this kind of a lattice, and all that. The net result is that you just get exactly what the fermion entanglement entropy thing is. This is a W infinity transformation, so I don't have time to go into that. why some local entanglement entropy in the fermion theory goes into some local entanglement entropy in the boson theory is a little weird. You don't expect such things in all kinds of dualities, that entanglement entropy is some local concept. It need not go into some entanglement entropy of some local thing. So I have explained. So this has to do with low energies. Okay. At low energies, you can show that this map, which looks absolutely horrible, and this is about the C equal to 1 matrix model. I don't have time to go to this, but if you apply the technique that I showed earlier, then you can show that all the finiteness arguments that I have given because of the finite value of the n here, in fact this is here this is double scaling limit. So you let n go to infinity, but this Fermi level, okay, you should let go, let this Fermi level go towards the hilltop, and some combination of these, the product of these is held fixed, and the result is that things are finite even at n going to infinity because of this other quantity being taken to 0, and its quantities are actually given in terms of that mu, okay, the double scaled quantity that is held fixed, and the mu gets related to this GSLS business. That is how the first result that I showed that comes out. And so here I have shown how things which look like integrals in the finite lattice, they become like these are the new things. This 25% that is new, this is part of that. It's an amazing thing. The lattice spacing remains finite, but the mode integrals, mode sums become integrals, okay, which must happen because there are infinite number of modes, okay. But the fact that there is a double scaling that is going on is weird. It's really weird, but it happens. Okay, so so this is the S matrix calculation. You can okay, all right. This is the D-brane stuff. So there is a D-brane interpretation of the lattice scalar that we introduced. Anyway, here's the conclusion. Oops, excuse me. Here's the conclusion. Okay, I'm done.